Okay? So it's exactly the same thing, right? Your stomach will say, sorry, I can't handle all of this. Give me one thing, right? Or two things. When you put a lot of these things, admixture-semen incompatibility is going to be there because these are all different chemicals. All these chemicals are acting in different forms, and we'll talk about some of those as we get there. Okay, proportions. Just some rough numbers of air entrained. I mean, this is the typical US. In the US, most concrete is air entrained. You will have some air in all the concrete because we have freezing and thawing in pretty much every part of the US, except for Southwest. But still, air is there in every concrete because we need protection from freezing and thawing. You will have freezing and thawing issues if you go up in the Ladakh, Leh, Kashmir, Himachal Pradesh areas. You have the same thing there also. So if you look at air entrained concrete or non-air entrained, you see roughly what volume percent is cement, what volume percent is coarse and fine aggregates. Here also you will see a little bit of air because even if you don't want to put in air, you will have some air. You see all these honeycombs and stuff in the concretes that are made. And then 30 to 50% of coarse aggregates, 25 to 30% of fine aggregates, 16 to 21% of water, 7 to 15% of cement, roughly by volume. Okay. Now, one of the important things that if you do concrete mixture proportioning, you always do by volume, right? Because you're putting in a volume of, nobody asks you for 10 kilograms of concrete. They'll ask you for 1 cubic meter of concrete. So if somebody asks you for 1 cubic meter of concrete, you have to design it for 1 cubic meter, not for the equivalent weight, because mass is not a good way to design anything. Okay, so simple. Again, food example is very easy to relate to. When somebody asks you, now you see this in airplanes, I have to correct myself. Normally when you ask, when doctor will say, right, if you have some disease and you have to control your food, they'll say 1 cup of rice, right? Volumes. But if you travel these airplanes now, they'll give you 100 grams of biscuit, 50 grams of cashews. Food was always in terms of volume. Now food is in terms of mass because they can charge you for mass easy. They can give you something of very high density and the volume would be very little. Okay, durability, we'll cover durability in one complete session on Friday possibly on what happens with damage and how microstructure relates to damage. Okay, so can we define concrete, or how would we define concrete? I've put in here 3 definitions. Definition 1, cement and water forms a binding medium with aggregates as fillers. Yeah, it's an introductory undergraduate explanation. BTech first class in concrete, maybe it's okay. Coarse aggregates are sort of mini masonry joined by mortar. Yeah, it's too fancy because nobody sits and joins different things. But the third one is actually the more appropriate definition if you want to think of concrete as a manufactured material. Okay? As something that you manufacture, it is simply a two-phase material. When I say two-phase, if I take a piece of concrete and look at it, I can, with my naked eye, distinguish 2 phases. One is a hard aggregate phase, and the other is a relatively soft cement paste phase. So it's two-phase material, hydrated cement paste aggregates. Property is governed by the aggregate, property is governed by the paste, and more importantly, property is governed by the interface. What's in between those? Here is where I talk to you about the weak link theory, right? When you join something, what is a weak link? The interface between them. If you take sand and paste, and aggregate and paste, and take 1 cubic meter of concrete, how many interfaces? Billions and billions of interfaces, right? You have so many interfaces, you're not dealing with 1 or 2. So it is interface properties that control a lot of different things. Now, how does concrete fail? Does concrete fail in compression? Is concrete weak in compression? No, it's weak in tension. Tension means what? Pulling. If you have an interface, what does pulling mean? Separating things. Very, very natural. Now, we'll deal with, when we talk about mechanical properties, the idea that the idea of compressive strength is totally wrong. Okay? In real life, nothing should fail in compression. Get the idea? If I push, so a compression means 2 atoms coming close together. When I bring two different things close together, why should they fail? Should they fail? But why are we still failing? If I take a concrete cylinder and compress, it's still failing. Why is it failing? Is it failing in compression? Structural engineering question. Yeah, it's failing in tension. How is it failing in tension? Because of the wonderful thing called Poisson's ratio. Right? When I have a longitudinal compression, I have a lateral expansion. Concrete expansion means what kind of stresses? Tensile stresses. It is that tensile stress that fails it, not the machine, the stress that the machine applies. But we don't want to change traditionally what is being told of as a compressive strength, so we still use a random number. Compressive strength of concrete is fundamentally, scientifically, a totally useless quantity. 40 megapascal concrete means nothing. 40 megapascal in compression means nothing. 100 megapascal in compression means nothing. It's just a convenience number because that one number masks my entire ignorance about concrete as a material. I say 40 megapascal, I think I've conquered the world. I completely have masked my ignorance in everything that has gone wrong in that concrete by showing it a 40 megapascal strength. I can have a big gaping hole in that concrete and still get 40 megapascal strength, right? Right? I can have all the dirt and all the unnecessary minerals in it, but I would have dumped 800 kilograms per cubic meter of cement and it will give me strength. But is that the concrete that you want? The question, so strength as an acceptance criteria, you and I can do nothing about it. This is entrenched deeply in the public psyche. We cannot do anything. He was talking about 43, 53 grade cements. In the US, there's absolutely no grade of cement. There's no 43, there's no 53, there's no 33. There's just type 1 ordinary Portland cement. Buy it, you will get some strength. That's it, period. Oh yeah, maybe 43, maybe 50. Nobody's worried about the strength of the cement. Because, very simple idea. If I know how to design concrete, I can design concrete from any strength cement. If I know how to proportion it, if I know, and we'll talk about that as we go through. If I know how to pack my particles really well, how many people can fill in this room? Equal to the number of chairs. But if you look at some private buses that are flying through, do they just fill in people with the number of seats? They pack in as many people. So I used to work in Bangalore a long time ago. So the conductor will say, go in, and there will absolutely be no space inside, but he'll still say, keep going in, keep going in. That's particle packing. You see these buses? That's packing. If you really pack things, when you pack more and more particles, you will take off the porosity, you will remove the porosity. When you remove the porosity, things get stronger, right? So it's about packing, not about the strength of cement. Cement is the glue that covers all these things together. If you put in 800 kilograms per cubic meter of cement, you will have a thick layer of cement around an aggregate. And if you take a piece of concrete and you see a really thick layer of cement paste around the aggregate, you will know what happens, right? So it's not the strength of cement that matters, but it's about how much of paste that is formed and what forms in the paste. So we'll take the third definition as a two-phase material. So from now on, we always talk about two phases and the interface. Okay? So when we do the microstructure, we have to define what we are talking about, two phases and the interface. Okay, any questions until now? Any questions? Very basic introductory stuff. All of you good with it so far? Yes. Good? Okay. So now, a very key idea. A very key idea, not just in terms of understanding, but in terms of application. For anybody who applies concrete. Why do we put concrete in place? To do a certain function, right? It has to carry a certain load. It has to cover a certain thing. It has to span a certain distance. You have a certain requirement when you put concrete for any application. So, the question that you have to ask is, and this is changing in India now from 20 years ago when I worked in the cement and concrete industry. When I was working, it was always about, I designed the first ready-mix concrete for the Birla ready-mix Grasim's ready mix plant in Chennai when they started it in 1999, no, 2000. Okay? Nobody had any clue. 3 admixture companies will come and tell mine is the best, mine is the best, mine is the Fosrock will come, Sika will come, BASF will come, my admixture is the best. Of course, because it is Grasim, there's no competition for cement, right? They have their own cement, so we are not talking about any cements. So, and then we're not talking about fly ash because their Malket plant had their own fly ash. So we were designing it, and it was very interesting. My general manager, who was in Bangalore at the time, came in and said, okay, you have to design this with 400 kilograms per cubic meter of cement. Okay, I should have 720 kilograms per cubic meter of coarse aggregate. And once 3 things he told me, I said, then you do it. You've told me everything that I should design, then what is there in it to design? Right? So that's called the prescriptive design. When you go to a restaurant and eat, again, I'll use a lot of food analogy because it relates to all of us, right? Food is very easy to relate. When you go to a restaurant to eat, do you tell them, put this much of salt in sambar, put this much of spice in this, I want a dosha that is 3 meter, or whatever, 10 centimeter. You don't say that, right? You just say, give me a dosha, I think it's going to be tasty, right? You leave it to the manufacturer to give you what you think should be given. And we have robbed the manufacturer of the entire confidence that he has in doing it for all these years. We have told him, put this. So if you go to any specifications in CPWD or any state PWDs, the specifications will be so long that all you need is basically a cook to just give you the concrete. You don't need an engineer to do it because it's all given. I want this much of cement, water cement ratio should be this much, the aggregate should be from that quarry, the fly ash should come from here, you should buy the admixture from that guy, it should all be mixed at certain temperature, the drum should rotate so many times and bring it. Why? Right? You've prescribed so many things that you've taken any option of getting a good concrete. Now, if you say all of these, when the concrete goes bad, what is that guy going to come and tell you? You asked for this. I gave you exactly what you asked for. Right? So we have been living in the prescriptive world for too long. It's changing now. In the US, a lot of it has changed. It's all called performance-based specifications. I'll tell the contractor, I want 40 megapascal strength. I don't care how you get it. Get that to me. And of course, 40 megapascal. If it's a pavement, I would say I want 40 megapascal strength. I want the pavement to have an initial surface roughness of so much. I want the pavement to have a certain rapid chloride permeability value so that it doesn't get deteriorated fast. You will give 3 or 4 more performance indicators, not prescriptive indicators. So what that gives is, if it's a cement manufacturer or a ready-mix manufacturer, if he's really smart, and if he says, okay, I can give you the performance with 40% of fly ash instead of 35, won't he do it then? Right? If he does that, is that not better for all of us? That is the training that we should have. The training of giving people the knowledge and the freedom to design things, rather than what did you learn in your college? What did Professor Emma Shetty's book tell you? Please copy that and give that back. We don't need engineers for that. We have enough of people who can just copy things from one place to the other, right? You go and sit in this document writer's office, in advocate's office, they copy from one paper to the other, right? We have enough of those copies. We don't need them. Engineers need to be thinking and getting new things out into the market. So prescriptive specifications have to go to a certain extent. Now, why are prescriptive specifications not leaving us? Because the engineer or the owner doesn't have confidence in the contractor or the producer. So if producers are all established big companies, big ready-mix companies who know what they're doing with good engineers on the board, and they come and tell a state PWD, okay, you want concrete, what do you want? You want this, right? I'll give you, don't worry. Then, and I'll take the risk of something happening in it. When they do that, and when that establishes, things will change. But I think we should collectively argue for, and this is one of the things that is in the document that I sent to Ministry of Surface Transport, which is in some dustbin now, moving more towards performance-based specifications. So if I say what I want effectively from my concrete is performance, right? However you do it, I want performance. So that's the question. So what are the effects of material properties on performance? That's something that we will look at in the next 3 or 4 days. What happened? Oops, okay. Battery is running low. Okay, so enhanced performance by design. We have to look at link between material properties and microstructure. That's what I said we'll do hydration. Now, we have to also know that concrete that looks alike or I put the same exact thing in this concrete and that concrete. Why is it different, right? And I always use the example of graphite and diamond. What is in graphite and diamond? Carbon. Would you pay the same price for graphite as you would pay for diamond? Oh, sorry, diamond as you would pay for graphite? No. Why? You get something in diamond that you don't get in graphite, right? You can gift diamond to somebody, try gifting graphite to somebody, right? Won't be a good experience. So same thing. Effectively, can I go and say, okay, don't worry, this is carbon, that is carbon, take it. Does it work? Well, it might work. If you have a really enlightened somebody who is receiving it, it might work. But generally it doesn't, because even though they are chemically the same, they are physically very different. Properties are very different. So when somebody comes and says, so here's a simple example. Again, I'm giving you tools to in your real life to argue with someone. Oh, how is this different? I put the same thing here and same thing here. Why are you telling me that it's different? You can ask the same thing. Graphite and diamond are the same thing, but they don't do the same job, right? So even if it's the same, chemically, physical properties might be different. Okay, cement. We'll start with cement, which is the core, strength-giving, structure-giving component of concrete. All of you know what that is, so I'm not going to go too much into that. History of cements, Coliseum. I'll share the slides with you if you want, so that you can look at some history. John Smeaton apparently designed or made the first recorded concrete in history in 1756, where he mixed powdered bricks and added pebbles as aggregates. So I got a PhD thesis from one of the universities in India to evaluate, which was exactly that. So they were using powdered bricks and then some pebbles, and they made, it was called some sustainable concrete. So I was thinking, what's the difference between that guy and John Smeaton, who did in 1756, where somebody else who did in 2012, right? Very similar. So again, we do a lot of recycling, reinventing the wheel, which is okay. Sometimes you may have to do it, but it's always important, especially for students and research scholars, to really, really know what has been done in the area, okay? You have to know really, really well on how to do a literature review. During my days as a graduate student at IIT Madras, I had to go to the library, a 20 paise per page photocopy, take all the old journals, sit, dirt, you sneeze, you get a cold if you sit in the library for 3 or 4 days because all the book stacks were so heavy and so dirty. You make copies of it, you go to your hostel room, you read it, you come back, you still don't get all the available literature. What about now? There was no Google in our days, right? There's absolutely nothing that you can't find. Now it's information overload, right? So you should be able to parse the right information and be able to collect all the relevant information. So your literature review, you should not be very broad and do everything in concrete. Nobody can do. But the topic that you're working on, you should have a thorough knowledge on that. And the way I check with my students is that they should know the names of the key people who have worked in that area. If I say a name, if I say, who is that I don't recognize, I know that he hasn't read the papers well. So you have certain key people who would have done certain things, and you should know them, because like Einstein said, we stand on the shoulders of giants who walk before us, right? It's important to recognize, and it's important to know. So just that. So history, while not very relevant in engineering generally, is important to know. He did mechanics on water wheels and windmills. Pressure velocity relationships to objects in moving air is called Smeaton coefficient. So he did a lot of different things. He was not a civil engineer at all. Hydraulic cements in 1796, calcining nodules of impure limestone containing clay in England. 1813, Whitegate. All of you remember that name? Whitegate apparatus. Artificial hydraulic lime with synthetic mix of limestone and clay, he slaked them. Portland cement is attributed to Joseph Aspdin. He was not trying to make cement per se. He was trying to mix limestone and clay to see if he can get CO2 out of it, because limestone has CO2. And then, lo and behold, it became a hard product. So he figured out that might be useful for something else. Portland cement is named after the Isle of Portland in English Channel. Natural limestone for cement manufacture was quarried there first. First use, like I said, John Smeaton. First patent, Joseph Aspdin in 1824 in the UK. In the US, first patent, David Saylor in 1871. So it's not a new material by any means. 1796 through 1871, all the research and discovery in Portland cement has been done. Okay, we are now just sitting and scratching the surfaces here and there. Aspdin was an English mason from Leeds. He did the patent in 1824. First cement works in Kirkgate in Wakefield, 1825. This is David Saylor's Saylor Park Cement Industry Museum in Pennsylvania in the US. This was how the first cement plant looked like. Okay, so ASTM C150, which is what we all use for standard for cement. I know, what is IS standard for cement? IS what?
Now IS 269 for OPC.
Okay.
For PPC it is 1489.
Okay.
For PSC is 455.
Okay. So you have all these different standards. In our world, there's only one, ASTM C150. We are done with it. Just one standard for all the cements. So fly ash and all, we have different standards. Okay. So hydraulic cement made by pulverizing a clinker consisting of hydraulic calcium silicates with one or more forms of sulfate in the ground. Very simple, right? Hydraulic calcium silicate with some sulfate. What do you need sulfates for? Flash setting, gypsum, addition of gypsum. That's all you need. So anybody who is in the cement business will know that. It's also very important to know. How many kilograms in a bag of cement? 50 here? 50. And how much does it cost? 400 rupees. So it's about 8 rupees a kilogram. What other material will you get a kilogram for 8 rupees in this day and age? Salt. I bought 100 grams of Tata salt for my mother, 18 rupees. 100 grams of Tata salt. Gandhiji said this should be free for everybody, right? But apparently it's not. What other material can you get for 8 rupees a kilogram? Nothing, almost nothing. How much does a cement plant cost to build? I'm just playing now the devil's advocate for cement manufacturer. I'm giving them the latitude to say that yes, we can increase the price further. How much does it cost to build a new plant? What's the newest plant in India that was built? Was it Reddypalayam? After Reddypalayam, did they build something else?
Recently it is in that Karnataka, North Karnataka plant, it is built with 4,500 crores.
Okay. Well, 4,500 crores. And how much does it produce?
3 million.
3 million. Reddypalayam was 1 million. 2 million. So 3 million tons, 4,500 crores. So you're spending 4,500 crores as an investment to sell something for 8 rupees a kilogram. Right? You should say it's a stupid business model. Who is trying this? But how do they make money? They know that you have no other option to build anything. Volumes. It's the volumes that speak of it, right? You have to use cement to build all the infrastructure that you see, billions and billions of tons required to create infrastructure. So there's no way that you're going to do anything else. Now, I'll show you a little more complex operational stage in a cement plant, and most of you might know it. So you have mining, blending, clinkering, cooling, grinding again, blending, shipping, all these things being part of just one single manufacturing operation. Typically, you might mine and leave it, right? Companies like Vedanta, they're creating big problems now. You heard that in Tuticorin. They just mine. They don't do anything else. They just mine and sell. Blending, you have companies that blend. Clinkering, high temperature clinkering, if you want an example, not really high temperature, but clinkering or pelletization, the drug industry. They get these compounds and pellet and give you the tablets that you eat, right? A controlled cooling, grinding, blending, shipping, all of these in one operation. And chemical compositions, when you do this, have to be maintained in very narrow ranges, right? Calcium oxide content, little high, you have free lime. Calcium oxide content, little low, not enough CSH forming in the reactions. Right? It's very, very fine balance of what you need. Basic constituents, calcium, silica, alumina, and iron, and then you have other minor elements. Very basic idea. Where do you get calcium from? Limestone, marble, shells, shale, but mostly from limestone. Silica from clay, fly ash, limestone. Alumina from bauxite, shale, slag. Iron from some iron ores and clay. Sulfates from gypsum or anhydrite. So classic way in which you get all your components. Now, typical numbers, I think these are all over the world. Calcium oxide 60 to 67%, silicon dioxide 17 to 25%, aluminum oxide 3 to 8, 0.5 to 6 iron, 0.1 to 4, magnesium oxide, issues with soundness if you have more oxides, alkali, sodium and potassium oxides 0.2 to 1.3%. Typically your IS standards or ASTM standards will ask you to keep it lower than 0.6. 0.6 now in India?
Yeah, 0.65.
0.65. In the US it's 0.6. So they'll ask you to keep it lower than 0.6. Sulfates 1 to 3%. So that adds up, and that's all what you have in this very complicated material. Now you have some complications. I'm sure you might have heard, all of you are familiar with these terms, right? C3S, C3A, C2A, and C4AF. So I'm not going to go into it. But again, make sure that you understand what this means so that we can, when I say C3S, you don't get confused. All of you good with this so far? Am I going too fast? Okay. Cement kiln. All of you must have seen cement kilns. If not, I would strongly encourage you to go and visit a cement plant. There are plenty of them around. What happens inside the kiln? This is something that I would just want to briefly touch upon because this influences the microstructure later on. So you have all the different materials that you put in, you throw into the kiln, and then you start heating it up, right? You want to get clinker out, but before that happens, until about 700 degrees Celsius, you have free-flowing powder. Your water is lost because you have a high temperature, and then dehydrated clay for alumina. Clay started recrystallizing, you have clay particles, you have limestone particles, water is being lost. 700 to 900, calcination happens, right? At about 800 degrees Celsius is when calcium carbonate becomes calcium oxide and carbon dioxide. About 800